Hello and welcome for day 4 of Unit 9. Today we are going to be talking about applications of and interpreting exponential growth and decay functions. So we've been kind of only focusing on this equation up to now. And that equation is like your standard form of an exponential. A usually represents the initial amount or your y-intercept, and B is either your growth or decay factor. But what you're going to find is when we apply exponential growth or decay to money or bank accounts or things like that, what they're going to ask you is not only the growth factor, but the growth rate or the decay rate. So by what percent is it decaying by over time? So that B, the base of our exponent, actually is going to kind of transform and look a little bit different. And you'll notice that there's this formula given in the problem. That formula is not going to be something that is on the reference sheet. That's usually something that I would say you have to memorize. But I hate using the word memorize. I'd rather you understand why the things are where they are. And the plus or minus, that is not, you're not going to use a plus and a minus sign every single time. If you notice that the situation, whether your bank account is growing, the bacteria are increasing, your car, your purchase of your house appreciates, you're going to use the plus sign if the amount is growing. So if it's an exponential growth situation. Sorry if you can hear my dog drinking in the background. You're going to use the minus sign if they use the words decay, depreciate, diminish, deplete, pretty much anything that starts with a D. That means you're going to use the minus sign. So that's going to be for our decay functions. Now you're also going to notice that there's different letters being used now. Remember, this is an application, so we are no longer going to be talking about just straight exponentials. We are now applying them to real world situations, typically applying them to money situations. So A is going to represent your final amount in your bank account, or how much money you will have, or how much population you will have, or whatever, after a specific amount of time. So I always think as A represents the after amount. The P, what we used to consider the P is our initial amount or our y-intercept. That's actually still exactly what it is. It is our initial or principal. Oh, I didn't spell that right. P-R-I-N-C-I-P-L-E. Principal amount, hence why they use the letter P, standing for principal or initial amount. But a lot of my students call this the pre-amount. Okay, so how much did you start with, your pre-amount? R is going to be the rate at which it's growing or decaying. But the thing is, if I'm going to say, hey, it's growing by 5%, you're not going to put a 5 in there. You're actually going to convert 5% into a decimal. So to do that, I usually just think of swinging the decimal place 2 spots and convert it. So if I swing 5 and convert it into a decimal, it becomes 0.05. So that would be what your R value would be in the parentheses. And then T is going to represent time. It could be years, months, days, whatever, and that's what you're going to plug in for T. So for this first section, all we are going to do is take the equations that are given. We are going to determine, first of all, if they're growth or decay, what the initial amount is, so growth or decay first, what our initial amount that we started with was, and what rate is it increasing or decreasing by. And once we know the rate, we should be able to determine the percent. So if I break this up, I'm going to rewrite this equation as 1, because that's the formula, 1 plus or minus a rate. 1 plus 0.2. If you can split it to be 1 plus something or 1 minus something, it makes it a lot easier. 4 is going to be our initial amount. 0.2 is going to be our R value. So now if I know the rate and I want to turn it into a percent, all you have to do is move that decimal place 2 times. And that would be a 20% growth. And I know that it's growth because the base, so that's G for growth, the base was greater than 1. So let's do another one where the base is greater than 1. So this is growth again because notice 1.05 is bigger than 1. So 1 plus 0.05t. So now it looks just like the formula at the top of the page. 12 is our initial amount that we're going to start with. 0.05 is our R. And so if I want to convert that to a percent, that would be 5% growth. So now let's make it a little bit trickier. Letter C. 0.92. That is less than 1, so we are talking about a decay function. So why I consider this trickier? Well, if it's decay, the formula would be 1 minus what equals 0.092. So here's how I do that. Take out my calculator, and if you are trying to figure out 1 minus what equals 0.92, just do 1 minus 0.92. There you go, 0.08. And you can confirm that those are equivalent things. So let me take out my calculator one more time. Is 1 minus 0.08 equal to the original base of our exponent? And that is exactly what it is. So now that I have that separated, this is my initial amount. My rate is 0.08. So the percent decay is 8% decreasing over time. All right, let's make it a little bit more complicated again. So letter D, if I split this up, 5 parentheses 1 plus what equals 2. So if I need to figure out 1 plus what equals 2, 1 plus 1 equals 2. Here's our initial amount. Our rate is 1, and you're thinking to yourself, okay, if my rate is 1, what percent is it increasing by? Here's where your decimal place is. Your decimal place is after the 1, so if I swing it 2 spots to the right, that is a 100% increase over time. All right, I'm going to skip E. I'm going to go to F. So yet again, we have a decay. So 1 minus what equals 0.2. So I go to my calculator, clear it out. 1 minus 0.2, enter. We are subtracting 0.8. Here's my starting amount. My rate is 0.8. What is that as a percent then? Swing, swing. So it's going to be an 80% decay. Hopefully that makes sense. We're going to do a couple more of these before we get into some applications, and I think you're going to like those. All right, number 2, given the following function represents an attendance at a music festival T years after 2010, by what percent does the festival attendance change each year? And does it increase or decrease? So when I'm looking at this equation, I'm going to rewrite as 1 plus 0.1t. And so by what percent? Well, here's the rate in the problem. R is 0.1. And so if R is 0.1 and I swing, 10% growth or increase each year. And I knew that because the base of this was greater than 1. Sorry, that's a G. How many people attended the festival in 2010? Well, 2010 is like our baseline year 0, our initial year. So if they're looking for our initial amount of people that attended the year in the first year, that is our y-intercept or our p-value. So 150,000 people attended it in its first year. How many people then will be attending, assuming that this growth keeps happening, 10% increase each year? How many people will attend it in 2014? So our formula has a T in it, but I am not going to plug 2014 because for T, because my calculator will assume that means 2014. If my festival started in 2010, and I want to know in 2014, That's 4 years later. So I actually am going to be plugging, oh no. I'm actually going to be plugging in a 4 for my exponent because I want to know what the future population is in 4 years. So, clear. All right, 150, 1, 2, 3, parentheses, 1.1, raise it to the 4th power, hit enter. And what does it say to round to? Round to the nearest 10,000. So my answer is 615. If it wants to round to the nearest 10,000, that would be this placement. So look to the right of it. Does the 9 round up the 10? And it does. So there'd be about 220,000 people that year. Number 3, the function represents the value of dollars of a comic book. The yearly rate of appreciation, growth of the comic book. So if I take this equation and I split it, it wants to know the rate. And clearly these are given as percents, so I'm going to convert my rate of 0.017 into a percent. So swing, 2 times 1.7%. And so my answer is option 2. All right, the population of buffalo has been decreasing over the past several years since the year of 2000. By what percent is the population changing each year? Is it increasing or decreasing? So if I take the population of buffalo, and it's obviously decay because it's less than 1. So 1 minus what equals 0.98. I'll take out my calculator. Stay consistent. So 1 minus 0.98 means I am subtracting 0.02. If I am subtracting 0.02, then the rate, swing, is 2% decrease every year. Using this model, how many people will live in Buffalo in 2020? So we started this model in the year 2000. I now want to go out to 2020. So if I subtract 2000 from 2020, I'm going to be plugging in 20 for T. So let's find out. The population, 0.98, 20 years later. I would type that in my calculator, and I get 195,609. Round to the nearest 1,000 people again. So I look to this. And does the 1,000, not 10,000. I look to this number, sorry. And does the 6 round up the 5? And it does. So my actual final answer would be 196,000. People living in Buffalo. Yay! All right, so what if I don't give you the equation right off the bat? What if I need you to plug everything in? So that's where we're going to finish off today, are these examples where you have to plug and chug. So remember, our formula is given here. A college tuition at Learn a Lot University increases. That's important, so we know we're going to use the plus sign for this one. Increases at a rate of 9%. If the rate is 9%, I need to convert that into a decimal, so 0.09. If the tuition for the university right now, its initial cost is $21,000, how much will the tuition be after 4 years? So that's time to the nearest cent. So what we're going to be solving for in this problem is A. I want to know after 4 years how much it's going to be worth. So my after amount is equal to my initial amount, 1 plus, because it says increases, my rate, raised to the 4th power because it's after 4 years. I'm going to type that all in my calculator at one time. So if I bring that back out, 21,000, 1 plus 0.09, and I raise it to the 4th power, hit enter, and it says round to the nearest cent. Nearest cent is 2 decimal places. Penny is 2 decimal places. So my answer will be 29,000 $643.21, so 21 cents. Okay, it's that easy. Once you know your variables that you're plugging in for, it's literally just plug and chug. Let's take a look at number 2. Andrew scraped his leg skateboarding. Today the scrape is 3.9 inches long. It has its size has decreased at a rate of 5% per day. So my rate is 0.05. What is the closest estimate of how long the scrape was initially? That sounds like an originally or initial whatever. So P, I don't know P. I don't know how long the scrape was, but it's after today. The after length is 3.9. If Andrew fell off his skateboard 5 days ago, so there's time, 5 days ago. So this time when I plug into my formula, I'm using the minus sign. I know the length after the 5 days. I don't know what the initial length of the cut was. The rate it's decreasing by is 5%, so 0.05, and this is after 5 days. So let's type in that part. 1 minus 0.05 raised to the 5th power. So if I do that, 1 minus 0.05, and that whole thing is being raised to the 5th power. Oh, I don't know what I just pressed. There we go. 0.77 yada yada yada. So I'm just going to put a couple of those down. 0.773778 dot 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 whatever. Save that number in your calculator. Divide that number to the other side. And you can solve for the approximate initial length, which was 0.504. It says round to the nearest inch, so I'm going to say 5 inches. All right, Karen received a diamond ring 3 years ago. Oh, this is another one where we solve for its initial value. Karen received a diamond ring 3 years ago. So that sounds like time to me. The current value is 1,500. So that's the current value. If the ring has increased, so we're going to use the plus sign, by 3%, so 3% as a rate would be 0.03. What was the original price? I don't know P. But I do know A because it's after those 3 years. Its after amount was 1,350. So let's fill in our formula. A equals P parentheses 1 increased, so plus the rate to the T. So again, you would just type in this part in your calculator. You get 1.0927 dot 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 dot. Divide that to the other side. Divide it to the other side. And you can solve for the approximate cost of the initial ring. So $1,235.44. And you can confirm all that in your calculator if you want. All right, let's do another depreciation one. So a lot of times your parents might say, once you get to the age of buying a new car, that cars depreciate the minute you drive them off the car lot. So Jerry's car will depreciate or lose value at 8% per year. So the rate of depreciation, losing, decay, whatever, is 0.08. He paid $15,000 for it when he initially bought it. So that's P. Which of the following is the closest approximation to Jerry's car's worth after 3 years? There's T. I don't know A. So that's my question, is how much is it worth now? So A equals the initial cost 1 minus the rate to the T. And all you do is plug and chug in your calculator. So if I type that all in my calculator all in one fell swoop, I end up getting 11,680.32. So I'm going to say the approximate cost is option 4. All right, let's maybe do one more here, and we will call it a day. Actually, these ones are pretty simple. We could probably fly through all of these, honestly. Number 5, the number of carbon atoms in a fossil given by the following equation is the function representing growth or decay. That should be a very easy question for us to answer at this point. If the base is less than 1, it is decaying. So part B says, okay, if it is a decay, what percent of change is happening each year? What percent is it decaying by? So if I want to go back to how we started today, 1 minus what equals 0.95, and it would be 1 minus 0.05. What percent is that? That would be a 5% decay. You could explain, all you would have to say is 0.95 is less than 1, and since 1 minus 0.05 is 0.95, I know that that represents a 5% decay. You would just literally put in words what we thought. Number 7 is very similar. The equation is being used to calculate money in a savings account. What does the 1.02 represent? 1.02 is bigger than 1, so it's got to be growth. And by what percent is it growing? Well, 1 plus 0.02, that's your rate. That means by 2% growth. And so there's your answer to number 7. I don't know what happened to my counting with these ones, but it's fine. And then last but not least, number 11. Grisham is considering the 3 situations below, and we'll read them in a second. It says, which of the following represents an exponential relationship? All right. Let's read them. Option 1, for the first 28 days, a sunflower grows at a rate of 3.5 centimeters per day. That sounds like it's adding. It's growing 3.5 centimeters each day, adding 3.5 to its height. Option 2, the value of a car depreciates at a rate of 15%. That sounds exactly like number 4 here. That sounds exactly like that example. So that one sounds pretty good to represent an exponential relationship. That would just be a decay. Number 3, the amount of bacteria in a culture triples every 2 days. That means it is being multiplied by 3. And we learned a few days ago that if something is being multiplied by the same amount over and over and over again, that is an exponential. So option 2 sounds like a decay. Option 3 sounds like a growth. And option 1, if it's just adding the same amount, that's a linear function. I want an exponential relationship. So 2 and 3 sound perfect to me, and that is option 4. All right, I will see you the next time for our last day of this unit.